Hello everybody, it's Dumplet here, and here's an item from Calculus. Credits to the MIT Integration Bee for this item. Evaluate the definite integral sine 2x times cosine of cosine x with respect to x from x equals 0 up to pi over 2. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now, although this question came from the MIT Integration Bee, the solution is actually relatively simple, only some bit of elementary knowledge in integral calculus and just a little bit of trigonometric identity knowledge. Now, the way to start is kind of obvious. We have sine 2x over here, and we have the well-known identity, the double angle identity for sine. So we have sine 2x, which is equal to 2 sine x cosine x. And we just replace sine 2x with this, so we will end up with this integral to evaluate. Now, whenever we see an integral involving a lot of sine x and cosine x, the first instinct for us is to do a u sub. Now, since we have a nested cosine x here, we want to simplify the integral, so it is best for us to have the u substitution u equals cosine x, at least to simplify this nested cosine inside of this cosine function. So suppose we have u equals cosine x, then differentiating both sides, we're going to get du equals negative sine x dx. Now let's go back to the integral. So since we have u equals cosine x, we would have du equals negative sine x dx. Now, we can obviously see here that we have sine x dx, which is this part, and then cosine x would be replaced by u, and this cosine of cosine x would be replaced by cosine u. So we have 2 times du, 2 times negative du, so this will give you 2 times negative du for the 2 sine x dx, and then we have u and then cosine u, and then we just simply rearrange the terms to get to this point, negative 2u cosine u du. Now don't forget to change our bounds, lower and upper bounds. So going back, since we're evaluating from x equals 0 up to x equals pi over 2, we simply put x equals 0 and x equals pi over 2 into the u substitution that we made. So at x equals 0, we have u equals 1. And at x equals pi over 2, we have u equals 0. So since we're evaluating from x equals 0 up to x equals pi over 2, our lower bound for the integral in terms of u would be u equals 1, and our upper bound would be u equals 0. So we have a higher lower bound compared to the upper bound. So we want to simplify this. So we can simply use the fact that we can interchange the bounds and then multiply negative 1 to this expression in the middle. So we can actually change it to the bound that we want from 0 to 1. And then we just change the sign. So we have 2u cosine u, cosine u du. And this will be easier to evaluate since we have a better looking integral. So we have 2 cosine u du. Now, surely we can also put the constant factor of 2 outside the integral, so it suffices for us to get the integral of this. Now, the integral of u cosine u du, this is just a very simple integration by parts exercise, and we can use the DI method, or the differentiation integration method, to help us get the integral easier. So we can put the table d and I. Now, since it would be easier for us to differentiate u, because we know that we differentiated twice, it's going to become 0, and let the thing to be integrated to be cosine u. So we have u and then cosine u here. So we put the plus and minus sign. I think we only need like 2 pairs. So u and then 1. You take we differentiate u. It's going to be 1. We differentiate 1. It's going to be 0. Now we integrate cosine. We're going to get sine u. And then we integrate it again. We're going to get negative cosine u. Now to get, we simply take the product of u and sine u. U times sine u with a positive sign is going to give us u sine u. And then next we multiply 1 and negative cosine u and we subtract it. So we subtract negative cosine u. So in effect we're adding cosine u. Now since this is 0, anything we multiply to here would be 0. So we will need to evaluate this. We will need to evaluate u sine u plus cosine u from using the bounds. So we need to evaluate this from 0 to 1. So we want to evaluate u sine u plus cosine u with the bounds 0 and 1. Now if we substitute 1 in this expression, we will get sine 1 plus cosine 1. That is for the upper bound. And then we want to subtract our result if we use the lower bounds, 0. Substituting 0 in this expression would give you 0 plus cosine 0. Now cosine 0 is just 1, so we simply get minus 1. So everything inside this bracket evaluates to sine 1 plus cosine 1 minus 1. Now note that the 1 and the 1 here inside the sine and the cosine are in radians. Okay, so it's not 1 degree, it's in radian. So sine of 1 radian plus cosine of 1 radian minus 1. So all we have to do is replace the bracket with this expression, and then we can simplify. So we have 2 times sine 1 plus cosine 1 minus 1. So we distribute the 2 to each of the factors, and we'll arrive at the answer that the original integral evaluates to 2 sine 1 plus 2 cosine 1 minus 2. And this is the exact answer. Now, if you're going to try to input the integral into Wolfram Alpha, Wolfram Alpha won't actually give you the correct or the exact answer, but instead give us an approximated answer. And if you want to check this via the calculator, this is correct to 6 decimal places. So we've successfully answered an item from the MIT Integration Bee that Wolfram Alpha cannot give us an exact answer. So hope you guys learned something new from this video, and I'll see you in the next video. Bye bye.